After studying this module, you shall be able to know what is optical activity, symmetry aspects of optical activity, example of disymmetric molecules, that absence of SN axis of any order means compound is optically active, conditions for optical activity, know about dipole moment, know about symmetry and dipole moment, general symmetry criteria for dipole moment in a molecule, some examples for finding the dipole moment. Optical activity has both classical and quantum mechanical roots. Of all the natural phenomena observed in nature, none has so profound effect on chemical thought as that of natural optical rotator power. Chirality or optical activity can be applied to molecular structures as well as to individual molecular species. Now, Boyd noticed that plane polarized light was rotated either to the right or to the left when it is passed through single crystal of quartz or aqueous solution of tartaric acid or sugar. Substances that can rotate plane polarized lights are said to be optically active. Those that rotate the plane clockwise are said to be dextrorotatory. Those that rotate the plane counterclockwise are called levorotatory. Pasteur in 1848 noted that sodium ammonium tartrate forms two different kinds of crystal that are mirror image of each other and rotate the plane polarized light. In this module, details of optical activity will not be discussed, only the symmetry aspects of optical activity will be taken. Criteria for optical activity of a molecule involves the test of superimposability of its mirror image on the original one. In slide 1, we are seeing non-superimposability of mirror image arrangement of tetrahedrons with different substituents. That is like this, we are having, these are the tetrahedron with two different substituents and these are the mirror image of each other. That is, if I put a mirror over here and then you will find in mirror it will look like this. Now, if I try to superimpose this and its mirror impose on this, you will find it is not possible to completely superimpose each other of this. So, earlier criteria we were using, that is, take the mirror image, try to superimpose, you will find it will not be superimposed. Then we say that this molecule is optically active. That is, this, so superimposed or non-superimposable property generally we used to look earlier. Now, what happens if I go on taking the case of mirror image and then it's superimposable on the molecule? Then if I have a complicated molecule, then it is very, very difficult to find a way to take the mirror image and try to superimpose one mirror image on the other. Also, there are various ways of writing these configurations. For example, if I take 2-iodobutane, C4H9N, and I can write down this into various projection form. Say if I take is 2-iodobutane, I can put down into various configurations as shown. Now, in one of the configuration, which is a planar one, it is like this, which I am showing over here. That is, in the plane of the paper, this is also the way we can show it by dotted line and solid line. Now, if we take this configuration, that is, we are representing by a planar structure with dotted line and solid lines. Solid lines means pointing backwards, that is towards me, and dotted lines if I say they are in the plane. Now, if I take the mirror plane of this molecule, if I take, it is like this, and after mirror image of this and try to superimpose on this, it is not superimposed, but one is tempted to rotate this mirror image like this and then try to superimpose, then it is superimposable. So, if we take this planar configuration, planar projection, then we find that is this is the mirror image each other, and if I give the rotation to this mirror image, I can superimpose. So, this misleads us to that the molecules is non-optically active. But we do not have such configuration, that is only this is the configuration, a relative position of each and every group is fixed. After taking this mirror plane, you can take this, you can give any rotation to this molecule, mirror plane, and try to superimpose, it will not be superimposed. So, stereochemistry is very, very important to in this case. Now, we have seen two difficulties, that is the representation of the molecule in different projection forms that can mislead us to the optical activity, and secondly, if the molecule is very difficult to go for the test of superimposability. Superimposability test can be easily performed for simple molecules, but when complicated molecules are examined, each visualization becomes more difficult and cumbersome, time consuming. There is a simple way of looking whether molecules will be optically active or not. Symmetry properties of the molecule can help in this direction. The earlier definition of a molecule to be optically active or not was that it should be asymmetric and should not have any symmetry elements in it. For a molecule to be optically active, it should not have mirror plane center of inversion. This definition has been now modified. All molecules which lack SN axis of any order will be dissymmetric and optically active. That is, the molecule and its mirror image cannot be superimposed in any manner, that is by rotational or translational motion of the whole molecule. We know that S1 is equal to sigma, S2 is equal to I. So, molecules having S1 and S2 axes respectively means that these have sigma and I respectively, and thus cannot be optically active. Optically active compound need not be asymmetric. These may have some symmetry axis. Let us examine this definition, that is the dissymmetric molecules having optical activity. For this, let us take the example of cis and trans 1,2-dichlorocyclopropane as shown. Cis form has S1 sigma, so it cannot be optically active. Trans form has C2 axis in the plane of 3-member ring system, bisecting CC bond bearing chlorine atoms and passing through carbon, which has 2 hydrogen atoms attached to it, that is ethylene carbon atom. As shown, these two are shown. Thus, trans 1,2-dichlorocyclopropane does not have sigma or S2 axis, so it is optically active. But transform and its mirror image have C2 axis, that is, they do not lack symmetry. These are disymmetric but not asymmetric, without symmetry element. The only symmetry elements that disymmetric, that is optically active compounds can have are one or more CN axis. Many diasymmetric compounds have C2 excess, but most optically active compounds are asymmetric as well as diasymmetric, hence have only C1 axis, Sn axis, n is greater to 2 is difficult to find. Example of molecules lacking sigma and I still optically inactive. Let us take an example of a molecule which does not have S1 or S2 in it, but still it is optically inactive. The example we take is that of Spiro compound 3,4,3-4- tetramethyl Spiro 1,1 bipyrrolidinium ion. This molecule does not have I, so it should be optically active. But it is not so. It contains S4 axis coinciding with C2 axis. This shows the presence of S4 axis into this molecule. Molecule does not have sigma, but combination of sigma and C4 axis results in S4 axis. Thus, the molecule is optically inactive, even if it does not have sigma, as it contains S4 axis of rotation. The S4 axis is shown in this molecule. Let us take another similar example of a molecule which does not have sigma or I in it, but still it is optically inactive. Example we take is that of 1,3,5,7 tetrafluoro octatetraene. It lacks both sigma and I. It is not optically active. This molecule has C2 axis and S4 axis along the C2 axis. All this molecule is shown and the various symmetry elements are also shown, and presence of S4 axis is also shown. Conditions for optical activity. Now, if the molecule possesses only Cn axis, it is disymmetric and optically active. If n is equal to 1 in Cn, the molecule is asymmetric as well as disymmetric. If molecule possesses Sn axis of any order, it cannot be actively active. S1 means sigma, S2 means I. Now let us take another properties, dipole moment of the molecule and symmetry. Now symmetry can help us to find the dipole moment of the molecule. For this, draw the correct Lewis dot structure of the molecule. Draw geometry according to this VSPR theory. Find whether the molecule is totally symmetrical or not. Polarity in a bond means pull in a particular direction. If the pull is equal, then there will be no polarity into the molecule. Criteria for dipole moment. If the molecule is diatomic and atoms are different, then there will be dipole moment in it. A molecule which just has one electron pair in it will have dipole moment. If all n atoms are similar and there is no lone pair in it, then the molecule will be non-polar. If the molecule is unsymmetrical, it will have dipole moment. Thus, we see that if we want to know whether the molecule has dipole moment or not, we have to go through these points and come to the conclusion. Here symmetry property of the molecules comes to our rescue, and just by noting the presence of symmetry elements, one can easily predict whether the molecule will have the dipole moment or not. Now symmetry properties of the molecule. Dipole moment is a vector property. It has both magnitude and direction, and it results from unequal sharing of electron between atoms of a bond in a molecule. It is a stationary and not a dynamic property. Stationary properties must remain unchanged by every symmetry operation of the molecule. In order dipole moment remains unchanged, dipole momentum must lie in each of the symmetry elements of the molecule. Molecule having I cannot have dipole moment, as vector cannot lie into the point. Molecule having CN axis only have dipole moment vector along CN axis. Molecules having sigma have dipole moment vector in this plane. Molecules which have more than one CN axis, n is greater than 1, cannot have dipole moment, as vector cannot lie along each and every axis at the same time. Molecules belonging to C1, Cs, Cn, Cnb only can have dipole moment. That is, molecules belonging to Cn having Cn and sigma V have dipole moment along Cn and sigma V. If dipole moment of a molecule is known, symmetry of the molecule can also be predicted. Symmetry arguments can only fix the direction of dipole moment vector. It cannot give its magnitude and cannot tell about the positive and negative ends of it. If one knows these points about dipole moment and symmetry elements present into the molecule, then one can immediately predict the structure or the direction of the magnitude of the molecule. Example of finding dipole moment using symmetry criteria. We can take the example of CO2, water, CCl4, F2SO4. Carbon dioxide CO2 belongs to D infinity point group. It has C infinity axis and N C infinity axis perpendicular to C infinity axis. Dipole moment vector cannot lie in each and every axis, so the molecule has no dipole moment. Water molecules belongs to C2V point group, has C2 axis and 2 sigma V. Dipole moment vector will lie along C2 axis and will lie in this plane. Let us take CCl4 molecule. It is highly symmetrical molecule. It has multiple axes of several order. Dipole moment vector cannot lie in each and every axis, so molecule has no dipole moment. Now let us take F2SO4 molecule. Now in the dotted line shows a mirror plane passing through oxygen and bisecting fluorine as F bond. So it has one mirror plane and it will have the dipole moment lying in this mirror plane. In brief, optical activity in molecules has been explained. Symmetry aspect of optical activity explained by taking suitable examples. Example of disymmetric molecule, cis and trans, 1,2-dichlorocyclopropane was discussed. Criteria for optical activity, that is the absence of SN axis, explained by taking suitable example. Some conditions, optical activity are also given and explained. Symmetry and dipole moment explained by taking suitable examples. Some main points about symmetry and dipole moment are given. Examples of take various examples of CO2, CCl4, water molecule, F2SO have been taken to explain the presence of dipole moment in these molecules.